Okay, so welcome everybody to the next session of the Introduction to Data Science PhD training. And today we are dealing with probability theory. We've covered some simple descriptor statistics, and now hopefully we've seen the need to do it in a slightly more formalized way to give proper definitions. So let's try to do just that today. Quick reminder that we've covered simple descriptors of location and spread. And for location or central tendency, there were several types, and for variability or spread, there was also several types. So plan for today is to deal with probabilities. And let's start with a famous joke. What's the probability to meet a dinosaur? 50%. Well, why? Either you meet the dinosaur or you don't. And that's one of the possible answers. And it can be a correct answer in certain circumstances because it depends on definitions. And what is interesting is that people always try to understand the risks, understand the probabilities, understand the luck. And at least from the 16th century, there were some attempts to formalize game theory, formalize the wins or the probabilities of winning. And then you can see there were multiple attempts and quite famous discoveries. But what is interesting is that only in the beginning of the 20th century, it was formally, properly written down as mathematical theory, starting by, well, amongst others, axioms introduced by Andrei Kolmogorov. And he did it by combining obvious and well-known probabilistic notions with well-developed by that time measure theory. And it was not the end of the story, because after it was introduced, many other people, Fisher, Newman, and so on, they developed that classical approach, rigorous approach, and which we know now as frequentist probability. And in the end, it turned out that probably it's not everything that we need, and that will be, I will touch on that later when we talk about hypothesis testings and things like that. And that's how other branches of probability appeared as well. Bayesian is the most famous one. But let's start with the classical mathematical notion of probability introduced by Kolmogorov. So it starts by the notion of probability space. And probability space is a triplet which consists of three parts. The first part is the sample space, or the set of elementary events, which is usually all possible outcomes in whatever we're doing or whatever problem we are considering. The next one is the event space, and that's set of all possible combinations of elementary events, or rather the set of all subsets that we can build from those elementary events. And the third part is the probability. And the probability is just a function that defines something, or probability, for all elementary events or their combinations. And importantly, and the new thing is Kolmogorov's axioms. So any probability should conform to those three axioms. So the first one is positivity. So probability should be positive or non-negative for any event. Another one is also sort of trivial, that the probability of the whole space, the largest possible probability, is 1, as we all know. We can't have probability bigger than that, but also that that number 1 is obtained for the whole set, for the whole space. And then additivity. We want that probability of the multiple events can be computed as sum of probabilities. Now that's also a very important property, which is sort of hard to match. For example, in Bayesian theory, it's slightly different, but I'll touch on that in a couple of sessions. Okay, so 3 of those axioms. So let's try to apply them in a very simple case of flipping coin. And suppose we have just a normal coin with heads and tails. And then what's the event space? Obviously it's heads, it's tails, but also by definition, we should consider all possible combinations, which means that we should also consider the event that something happens, event that consists of both head and tails. And also we should consider an empty set, which means that nothing happens at all. And it can be any kind of impossible event. The coin disappears, or the coin lands on the side. So that should also be included when we define probabilities. And for a fair coin, as we all know, we just define the probabilities of heads being equal to the probabilities of tails and being equal to a half. Pretty obvious. Okay. So let's try to apply our knowledge. Suppose we flip a fair coin twice. Let's find the probability to guess at least one head. And it's a very simple problem, so I'll do it quickly myself. So probability of having at least one head is a probability of having head on the first flip, or probability of having a head on the second flip, and each of them is equal to 0.5, which means that the whole probability of having had at least once is equal to 1. What do you think? Is it correct? And as always, you're welcome to answer in a chat. So do you think my calculations are correct? No. What's the problem? Why do you think? Yeah, there are two questions in here. So why do you think that it's not correct? How can we clearly understand that it's not a correct answer? Yeah, that's the easiest part, because there's non-zero probability of getting something else, yeah, getting both tails. But then now there's second part. Where's the catch? Why? Where did I make a mistake? So any ideas? Why did I get the wrong answer in here? Right, okay. It turns out that we need only disjoint event to be able to add them up. So let me remind you that the third axiom said that we can add probabilities together, but it works only for disjoint events. And here, having had on first flip and having had on the second flip are not disjoint or mutually exclusive events, because we can have had on both coins or both flips. So that's a very important notion. That's why there's a separate name for those disjoint events. They are called in probability theory mutually exclusive events. And basically it's the same. If any two of those events cannot happen at the same time or simultaneously, we call them mutually exclusive events. And that's quite convenient because this definition also allows us to define so-called complementary event. And complementary event is just everything that is not in this event, everything that is mutually exclusive with this particular event. Well, for example, if you have heads on a coin, then the tail will be mutually exclusive and complementary event to it. So this theory, in fact, can be improved or can be generalized. And in fact, measure theory is a very wide subject. And probability theory just follows the same structure as we have in fields. So if you consider the family of events, it's the same as considering family of subsets. And then we can say that it is an algebra if our set of subsets contains an empty space, and when it's closed under some operations. So, for example, closeness means that it turns into itself. It doesn't turn into something else. That if we take the set of those operations, then we are still dealing with the same family of subsets. If we have the situation when everything is closed under infinite unions or under the infinite sums, it's called the sigma algebra. And such a pair is called the field of sets. Well, that's just a taste of how it can be developed and how it's connected to wider mathematical notions. But I'm not dealing further with it. It's just opening the door to probable other developments in that direction. Okay, so we've introduced the probability, and there are some useful but very obvious consequences. And just to try, I wrote the definitions for them. For example, the probability of complementary events can be computed as 1 minus the probability of event, and it can be formally derived from the axioms. And I really advise you, if you have time, try to repeat those derivations by yourselves, strictly from the axioms. Then the probability of an empty space is equal to 0, which, let me notice, was not in the initial axioms, but again can be easily derived from them. And it's all trivial, but please do check those properties if dealing with machine learning. Because in machine learning, well, it can be considered as sort of extension of classical statistics, which means the statistical rules still should apply there. But I've encountered many cases where people do not check them. For example, people get some kind of contingency table, and the numbers in this table add up to something that is bigger than 1. So, and probability of an empty space sometimes also is not 0, which is particularly interesting. So test your machine learning tool on something like a completely black square. That's quite a good test. So we've discovered that the sum rule works only for mutually exclusive events. But we would like to have more than that, and luckily we can, because there exists a general sum rule which says that we can find the probability of the union of two events by firstly adding the probabilities of them, but then taking away the bit that we've calculated twice, that is taking away probability of the intersection. And it can be described on the famous, well-known Venn diagram if we think of those events as of sets or as of circles on the picture. So to find the whole area and think of probability as of area. To find the whole area, we need to combine two areas, but then we need to take away the middle part. So let's try to solve the previous problem in a correct way now. So when flipping a coin twice, we have 4 elementary events all in front of you, and they have all equally likely probabilities of equal to a quarter. And then we can use the sum rule, and the probability of having at least one head will be indeed the union of probabilities of having head on the first flip and having head on the second flip. But then we need to take away the intersectory part, which consists of probability of having both heads on the first and on the second. And then our probability will be not 1 anymore, but 0.75. Much more reasonable, isn't it? Does anyone know another way of doing the same problem? So this time we just considered all possibilities, all 4 of them, and computed the found the total probability using the sum rule. Yes, thank you very much. Absolutely, we can use the complementary event and take, well, that's then we should have the similar answer. Or we also can consider all 3 of them one by one. And since the probability of each of them is a quarter, then combination of them will give 3/4, exactly as we did before. So we found intersection just by looking at it. We didn't introduce a formula for it yet. So the question always is it an easy way to find the intersection of events from the knowledge about what happens in some of the subsets? It turns out that yes, but only sometimes. More precisely, we can do it for so-called independent events, because by the definition, events are called independent if the probability of intersection can be computed as product of probabilities. And that formula is describes probability of the intersection or product, and it's also known as product rule. In practice, another thing happens. In practice, we often assume that some events are independent and then use this product rule. And it's particularly useful because it's easy. But can we always do that? Well, we'll see today what happens if we just blindly follow this simplicity. There are interesting cases of independence, and the notion of independence is, I'd say, a cornerstone of almost everything in math, not only in probability, but in probability in particular. So the first question, can an event be independent with itself? What do you think? A bit crazy question, isn't it? Can I be independent from myself? Can anyone be independent from themselves? What do you think? Well, yes, it's a crazy one, isn't it? Well, it turns out that generally you are correct, but there are very unique cases. That is when an event is an empty set, or when this event is everything that goes around. And then it turns out that indeed, formally, they are independent with themselves. Pretty interesting, isn't it? Another question. Can an event be independent with its complementary event? That is, everything that is not this event. Everything that complements this event to the full probability space. What do you think? And then again, we can try to apply the definition. So we will need to see what is the intersection of event A and its complementary event. So what's the intersection of events A and not A? Yeah, probably the question is too obvious, or everybody is waiting for yes. Yeah, absolutely. It's null. And what does it mean? Empty set. Yeah, and it means that basically we'll have the same situation as before. It's indeed an empty space, which means the probability is equal to 0. And the question is it possible? And again, it is possible only in those unique cases. And then the third similar question. How about in general, mutually exclusive events? Are they independent? Let me remind you that mutually exclusive events are the ones who have an empty space in the intersection. Well, and analogously, we can see that in this case, exactly the same mechanism works. The probability of the intersection is the probability of an empty space, which is 0. So in which case is it equal to the multiplication of two probabilities? But again, similarly, it will be equal to 0 if and only if one of them is 0 or impossible. And that's absolutely trivial, but I can't even mention how many times those two notions are mixed up. That's a very, very, very known problem. And not only in students, not only for students, because in papers and in quite complicated statistical applications, again and again, mutually exclusive and independent events are just mixed up. And what is the result? Well, we'll also see in a while. But let's try to apply our knowledge to some kind of a problem. Let's try to solve this problem. I'll give you a couple of minutes. What is the probability of having 2 heads in 4 coin flips? And there are several ways of doing it. So I'll give you a couple of moments to think about it, how we can approach it. And it is possible to solve it via multiple ways. For example, using the sum rule, the product rule, and write down what does it mean to have 2 heads out of 4. And then take away everything that gets in the way. But I wanted to demonstrate just quickly another possibility, which is to consider all possible basic events and to demonstrate how many of them we'll have. So on the first throw, we can have either heads or tails. And here in front of you, that's just a tree which appears if on the first throw there is heads. So it's half of all the possibilities that we are getting. And the similar tree, starting with the tails, will be exactly like that, but having T here and T instead of H on the first place. So amongst those half tree, we see that 2 heads will be in those 3 cases. And in total, we have 8 cases in front of us, which means that we have 3/8 probability. And for each of them, since we have in total 8 here and 8 in other half of the tree, in total we have 16 events, and the probabilities will be equal because supposedly we are dealing with a fair coin, and we can multiply the probabilities because all flips are thought to be independent. That's another important bit of that. And because all of those 8 and 6 in total in the whole tree events are mutually exclusive, we can just add up the probabilities. And then the total probability will be 6/16, 3 here and 3 on the other half. Okay. So drawing a tree for probabilities is also quite a common thing, just to be sure that we see all possibilities, but it takes time. But I think Bayesian theory in machine learning is essentially based on that kind of things. Well, there are more important consequences of the axioms, which we all know about, but it turns out that we can, again, just derive them from the three axioms that we wrote before. So one of them is that probability is between 0 and 1. Let me remind you that we did not ask for it to start with. We just asked for probability to be positive and the probability of the whole being equal to 1. But it turns out that we can derive the rest. And the next property is also well-known, monotonicity. So if one event belongs or is a subset of another, then the probability of a smaller event that consists of fewer amount of possible outcomes will be smaller than the probability of a fuller event. Also quite an obvious property, but also quite important. Okay, so let's try ourselves on the following problem. So suppose we have a probability of rain on a Saturday as a quarter, and on Sunday assume that it's not dependent on the previous day, and it's also a quarter. So what will happen during the weekend? Will we be lucky to get the probability of rain less than 50%? So will it be a nice weekend? So what do you think? So let's try to solve this problem. And can you please put the replies in the chat? So what is the probability of rain? Okay, so there are different ways of solving this problem. And one of them is to use the complementary event. And that will be, so we are interested in the probability of rain. And it's easier to find the probability that there's no rain, which will be 1 minus probabilities of no rain. So it's 7/16, which is smaller than a half, which means that the probability of rain is not so large, which is very good, isn't it? And another way of doing the same thing is using the sum rule and just finding each of the probabilities. So the probabilities of rain on one day, the probability of rain on another day, and then combine the probabilities. But please do remember to take away the probability of the intersection. That is the probability that both on Saturday and on Sunday it will be wet and nasty. And the main thing is that the answer should be exactly the same. Any questions? Yeah, I think it's pretty clear. So let's move on. Things are getting much more interesting if we are considering more than two events. And it turns out that we can consider mutual independence of a larger amount of events. And it turns out that we can define different kinds of probabilities for them. The first kind of probability of independence is pairwise independence. And the events are called pairwise independent if, well, any pair of them is independent. But also there exists the definition of mutually independent events. And let's see what it means. It says that probability of any kind of intersections of those events should be equal to the product of the relevant probabilities. So for example, for three events, mutual independence means that we should have all pairwise independences, but also at the same time, we should have the last probability of intersection being equal to the product of all three probabilities. Oh, and similarly for four events, we should have all possible intersections covered by the same or similar rule. So let's see why we consider different definitions. And let's see it on this example. Suppose we have four equally likely outcomes, and you can think of them as a result of some kind of binary machine that gives out numbers, or as results of coin throws with heads equal to 1 and tails equal to 0. Well, it doesn't matter. So suppose we have four equally likely outcomes and nothing else comes out of place. And suppose our event denotes 1 on the relevant place. For example, A1 will be 1 on the first place, which means 101 and 110. And A2 is similarly 1 on the second place, which means the second in the list and the fourth in the list, and so on. And the question is, are the events pairwise independent? And if they are mutually independent? So let's have a look. We can consider all possibilities. So A1 I spelled out, A2 I also spelled out, A3 is in front of us. And as we can see, each of them consists of exactly two events, hence probability for each of them is a half. Good. So what will be the probability of A1, A2? Yeah, very good, absolutely. So what can we say? Are A1, A2 pairwise independent? We can see that probability of A1 and A2 happening at the same time consists of this event, and the probability is 1/4, exactly 0.25, which means that it is equal to a half multiplied by a half, which is equal to the product of probabilities A1 and A2. And we can see similarly that for other events A, the same is true. So that means that all probabilities are pairwise independent. Very good. Now, how about mutual independence? What will be the probability of A1, A2, A3? Yeah, it would be nice, right? Have it equal to 0.125. And we could say that it is equal if we assume that those are independent, yeah? But let's try to remember what our events actually are. So the first event consists of 101, the third event in our list of 4, yeah? And the last one. A2 consists of 011 and 110. And A3 consists of 101 and 011. So the question is, which of the events out of our 4 events, which of them belongs to all 3? A1, A2, and A3. In other words, what is the intersection of A1, A2, and A3? Which event belongs to them all? Yeah, exactly. So there's no event that belongs to them all, which means that the intersection is empty, which means that the probability of the intersection is equal to 0. So is the probability of the intersection of 3 of them equal to the product of probabilities? Quite obviously no, because the product of probabilities is indeed I would covered a different one, is indeed 0, and the product probabilities will be 1 over 2 cubed. So they're not mutually independent. That's quite a famous example of having pairwise independence, but without mutual independence, to demonstrate that those notions are different. But the more interesting question appears if we try to have a look, what will happen if we remove just one of the elementary events from our list? If we leave only 3 of the events without the first one, then we can see that the probabilities of the intersections will consist of one event, exactly the same one as before, but the probability will be not 1 over 4, it will be 1 over 3. And similarly, the probabilities of all the events will change. They will consist of 2 events as before, but numeric value will swap from 2 over 4 to 2 over 3. And look how interesting. Just by removal of one of the events, which, by the way, did not belong to any of our events, just removing 0, 0, 0 case, which did not belong to A1, A2, or A3, we changed the mutual and pairwise independence of them. And that's an interesting property, isn't it? And that's why we should be careful when dealing with independent events. Just one small change in a subgroup, which we did not deal before, can change the whole independence things quite dramatically. Well, was it just because we had 4 events and then removed one and changed the number of events? You're welcome to try it by yourself and see how the things will change if we add back, say, 100 instead of 3 zeros. Just have a look and see what happens. But all in all, independence is a very interesting notion, and it's not a given. So if we remove just one sort of independent observer that did not belong to any of the events in question that we were particularly interested in, it turns out that it impacts all other independencies. And also we've seen that pairwise independence would not imply automatically mutual independence, Geometrically or graphically, it can be illustrated by the following three famous Borromean rings. Any two of them, if you look closely, any two are unlinked, but all three of them become linked with each other. So be careful when dealing with independence. Do not take it for granted, even for a simplified formula or simplified structure. Any questions in here? But yes, independence is a very, very, very famous notion and very important notion. As mentioned, it was used mostly to simplify the calculations. But unfortunately, being not careful with independence can lead to all kinds of problems. For example, it is thought that using independent events in everything just to simplify the formulas was one of the cornerstone problems of the famous financial crisis in 2008. And all of the models that tried to model the risk in mortgages, they assumed independence, which is a very, very sort of natural thing to assume. Homeowners usually they repay their mortgages sort of independently from each other. Well, why not? Well, now we know why, because in a crisis, well, people are never truly independent. Usually the dependence is quite small. But in time of crisis, this independence is just much, much easier to, well, the failure of it, much easier to trace. So in crisis, people tend to lose their income at the same time, and it becomes obvious that they do not really behave independently. And a nice illustration was shown in a big short film. And if you haven't seen it before, well, just watch it. It explains the very same thing, but in a very nice and easy terms and a picturesque way. So is it only in finances? Well, unfortunately not. Another example, which I faced quite recently, was in epidemiology. So the Global Burden of Disease project, which aimed to evaluate the number of diseased people in the whole population in the world, the projections or predictions or estimates were based on a so-called Dismod model to estimate those numbers. But the thing is that one of the main assumptions was that deaths from different diseases happen independently. So let's think. Is it a reasonable assumption? What do you think? Are deaths from different diseases do they happen really independently? In common sense, they are, right? That's what we would say. But let's think. If one death happens, can we die from another cause? Well, usually no, if you're considering just the primary causes of death, which means that in fact, deaths are not independent, they are mutually exclusive. So what did we learn about mutual exclusive events? Can they be independent? Well, sort of yes, but only if one of them is not possible at all. Or in other words, if one of the deaths is from some not existing or not dangerous disease. And in general case, that sort of means that we can die many times, this kind of assumption. If we can die independently, then we can die many times. And in a dynamical model, that leads to the whole bunch of different wrong predictions. Why? So the basic sort of so-called state model looks like that. And that, by the way, was one of the models that was used in modeling COVID, where we heard about R values and things like that, that actually came from this kind of modeling. So a classical state model considers several states of a population of a person. So here it's a healthy state, a diseased state, and then some kind of death. Death from this disease, but also death from other causes. And what happens after the first year? Suppose we have 100 healthy people, and suppose we haven't counted diseased or deaf people yet, and we have all zeros, and start to trace what happens to healthy people. So in the second year, it happens, so 10 of the people became diseased, and we had 10 deaths as well, 2 from this disease and 8 from other causes. All nice. But what will happen if we ignore the diseases from other causes and think that we can not include them in the formula? Well, we try to estimate the number of diseased, which is usually hidden, because usually in statistics, we know just the initial number and then the number of deaths. And we try to estimate the number of disease from the number of deaths. So if we ignore the amount of deaths from other causes, because assumingly they are independent, in fact, we consider everybody going through the diseased stage. As you can see on those simple numbers, we are getting over estimations. And that's well handy at some point, because we can sort of claim more money for our diseased people, even if they don't exist. But in long term, it can backfire, because if we pretend that we know for sure the exact numbers of diseased people for certain diseases and try to do financing based on that, then we will run out of money pretty quickly, and then we'll have no money for something else like social care or for research or for some kind of other developments. And unfortunately, that's exactly what's going on. And that particular DISMOD model was discontinued because it was noticed that it produces not very good estimates. Well, who thought? But unfortunately, other models, the way the system works, other models were calibrated on that one. And those models are not discontinued. And for different reasons, models that were calibrated or had the parameters matching the DISMOD models, those are still producing some predictions. So quite recent events with the recent predictions from a model that definitely was calibrated on DISMOD scared everybody with quite high predictions for major illnesses. Well, that's how it goes. That's why mutual independence, mutual exclusivity and independence are very non-trivial questions. So I was going to talk about another well-known paradox that is about probabilities to finding another person with exactly the same birthday. So we'll see how much we can cover in the remaining 10 minutes. And that's known as a birthday paradox. But today we'll deal with a slightly simplified problem, considering not the probability of finding a person with exactly the same birthday in a year, but probability of finding the person with the same day of birth in a week. So suppose we have, we have 7 days a week. So what is the probability that one of them has a birthday, say, on Monday? And how is it compared to the same question for 2 people? We don't have much time, and we seem to be a bit quiet today, so maybe I'll just move on. So since we have 7 days a week, then for one, the probability of having their birthday on Monday is 1/7. Two people, if they're truly independent, then their birthdays will be on Monday with probability 1/49. So quite a small probability. And we can imagine that the more people we have, the smaller this probability will get. No surprise in here. But let's change the question slightly and ask what's the probability that some 2 people taken at random will have the birthday on the same day of a week. So how is it different? It can be any day of the week, not a particular day of the week. So let's try to think. What is the probability that the first person has a birthday on the same day of the week? And it's a meaningless question, isn't it? Because the first person can have their birthday on any of the days of the week. Only if we have a second person, then this question makes sense. And the whole play is around that. So for the first person, we can choose the first person in 7 ways. Not interesting. But if we add the next person, then it's not independent from the first person anymore, because we want to match them, which means that we violate independence, which means that we need to compute the probability of this event in a slightly different way. So in this particular case, we can think that the second person it's easier to compute the probability that they are on different days. And then we'll find the probability of a complementary event. And for that, the first person can have the birthday on any day, and the second person should be chosen in 6 different ways, except of that particular day that the first person had their birthday. And then the probability of having different birthdays on the same day of the week will be equal to 1 minus 6/7, minus the probability that they have different birthdays. I think that's pretty obvious. Now, what happens next? Suppose we are increasing the number of people, and we are trying to find the probability of matching birthdays if we sample not only 2, but a larger amount of people. So what will be the probability out of n people to have at least 2 birthdays on the same day? And again, we can approach it in a similar way to find the complementary probability. There is a probability that they all have different birthdays. And approaching it in the same way, we can compute that it should be equal to the 7 multiplied by 6 and so on, divided by 7 to the power of n, because the first person can have a choice of 7 different days to be born. The next person to have a different birthday has a choice of only 6 remaining days, and so on, till we have sort of none left, or till all people are exhausted. So in a general case, this probability that at least 2 coincide is 1 minus the probability of all different birthdays. So for example, for 3 people, this probability of having at least 2 birthdays is 40% approximately. And it's sometimes a bit higher than we usually expect it to be. So the next question will be, what if you want this probability of having the same birthday to be quite high, precisely more than 85%? What minimal number of people or students we need to ask to find at least 2 who are born on the same day? So let's apply the same method. We know that this probability can be derived by this formula. And we've seen that this probability of having the same birthday for at least 2 people is always increasing. So the question is, when will it be more than 85? And you're welcome to check that. But it turns out that already for 5 people, this probability will be higher than 85%. And it's sort of, so we need to ask just 5 people. And if we choose 5 random people, then there's quite a high probability that they will have the birthday, the same birthday of the same day of the week. So the general birthday paradox deals with all possible dates of birth in a year. And it turns out that the number of people that we should ask to find amongst them with quite a high probability 2 with the same date of birth is unexpectedly small. So for 7 days, this number was just 5. For 365 days, it's also not as large as we would think. And why does it contradict our intuition? Well, because quite often we are thinking about a different problem. We don't deal with probabilities, we are dealing with certainties. So usually we are thinking in more certain terms. For example, what is the number of students that we need to ask to guarantee that at least 2 of them will be born on the same day of the week? And that's the question to you. So what is the number of students, the minimum number of students, that will not only give some probability, but to guarantee that at least 2 will be born on the same day? Well, guarantee will mean 100% probability or full certainty, and we can understand that from a so-called pigeonhole principle, we need to exhaust all 7 possibilities, all 7 days, and then add one more. And indeed, for this particular problem, to guarantee that to have 2 birthdays on the same day, we need to ask 8 people, and for a year, to guarantee that 2 people will have the same birthday, we need to ask 366 people. But probabilities are different. And for quite a high probability, this number can be substantially smaller, which is also related to a so-called dimensionality reduction principle, which we will cover in one of the next sessions. I think I'll skip that bit. So what we covered today, we covered some axioms, and we covered something that follows from the axioms but is non-trivial, that is the sum rule, how to calculate the probability of a combination of 2 events, and the product rule, and also which of the events can be called independent and which of them can be called mutually exclusive. Any questions? If there are no questions, then there's a homework problem for you to try yourself one and to think if the assumption that you make behind this problem is reasonable and what will happen if this assumption is not true. Because next time we are dealing with a case when the probabilities are not independent, and that's the whole new lot of so-called conditional probabilities. But that's all for today. Thank you very much. Any questions?
Olga, thank you. You could stop the recording and just in case invite questions after that. But keeping the slides in case.